Yeah, so really what this lesson is meant to cover is kind of just the basic design principles that you'll need to know for this team. So really whether you're in like vehicle dynamics, powertrain, chassis, or even electrical and software, your projects will almost definitely involve some of the concepts that will be discussed in these slides. So it's really important that you not necessarily know everything that's in here, but know generally like that these kinds of things exist. So that being said, if questions do come up, again, you're more than welcome to just kind of interrupt as I'm going. I want to make sure to answer questions as they come up. So for for context of what is happening, so again, these are really the basics of what you'll really be using in your time as you're designing. And this is going to go through the content of a lot of different classes. So as you can imagine, there will be a lot of stuff here. But again, no pressure to memorize all this stuff. Just know that it generally exists. So a lot of this will come with time and practice, but I figure it is best that we just kind of brush upon them as we go along. As with all lessons, slides and will be posted towards the end as well as the recording. So hopefully later, sometime later today. No, okay, yeah. So with all the topics, so there's going to be a number of ones mentioned here from different classes. Some might be covered more than others just because there will use some more than others. So we're going to be going through things like basic statics, solid mechanics, linkages, machine elements, methods of joining, which are kind of highlighted in the manufacturing class, as well as thermo/fluid stuff. Again, this is a lot of courses in the MEC curriculum, and it'll be a bit of stuff to cover, but we'll be going through it quickly. First things first, statics. So one of the most important reasons why it's like why knowing statics and having a knowledge of it is very important is that you really understand the forces and the moments on parts of a system. So kind of like if you have, well, let's say a static system or one where you know where the net force or moment, which I'll talk about more in a bit, is zero, you're really able to figure out as many of the forces as possible. This is really important because you need the force to know the forces on a system before you do anything else, especially because you don't want any parts that you make to break. That's the last thing you want. Additionally, there are some cases where it might not break, but it might deform, and you also generally want to avoid that. So with forces in a system, I mean, a lot of you know this by now, but it's important to kind of put these concepts down right now because they're kind of really what drives a lot of this stuff in statics. So as most of y'all will know, a system with a no change in linear speed, so it's basically not accelerating, has a net force of zero. Likewise, a system with no change in rotational speed, so it's not accelerating angularly, has a net moment of zero. Both of these are true for a system that is not moving or like just one that's in equilibrium. It is very important because with a lot of different systems, you're able to actually break them down into various points in time when they're actually essentially not experiencing any net force or any net moment. So this gets to be really important with things even as simple as brakes. And as we go along for each of these topics, I'm going to try to relate it back to the car as much as possible, because ultimately you're going to use a lot of these things to really come up with a design of the car. So for the brakes, there's actually a lot that has to go in terms of the designing of the pedal. We firstly want to make sure that when we press it, it doesn't break, but we also want to make sure that when we press it, that the proper amount of force is being applied. This is kind of a very brief rundown of how the brakes work. This will be talked a bit more about later, but essentially you have a pedal which presses on the master cylinder, which is up here, and there's this long tube that creates pressure in the system and sends it over to the brake calipers. The brake calipers essentially have two pistons which kind of clamp down on the on what's called a rotor. Essentially, the rotor is attached to either to the essentially generally to the hubs or to axles, and if you clamp down on them, it creates a lot of friction, which stops the rotation of the brakes. And in order to accomplish all this and make sure that the brakes actually stop the car and that you don't just kind of keep going, you want to make sure that you're applying enough force. And so, kind of just doing an analysis of the pedal as is, we would be curious to find out what force we're experiencing in the master cylinder. So the reason why we have this 450 pound force on the pedals, because that's actually specified by the rules. The rules state that the entire braking system must be able to handle a 450 pound input. I don't really see why that's necessary, because I don't think really people are going to be applying that other than possibly like Phil. For context, Phil, when he was bleeding the brakes, kicked the brake pedal and kind of deformed the mount. That was a fun time. But continuing on, with that 450 pound force on the pedal, when you're looking at the pedal, you can actually break it down into a type of a lever, where the pivot point is where both of these dimensions meet up. I don't know if people can see my cursor, if someone can just drop that in the chat if that is the case. Okay, cool and good. So yeah, over here is where you can see is the pivot for the pedal. So as this gets pushed in, the top of the pedal pushes the master cylinder in. And so this essentially creates a lever where one arm of it is 6 inches and the other is 1.5 inches. So we always treat the system as, especially like let's say when the driver is pressing on it fully and the brakes are completely actuated, we're treating that as the scenario in which there's the maximum amount of forces. Because in this case, if everything's static, you know that you're getting the maximum amount of force that you can, or reaction force from the master cylinder. So we treat the system as static and we say that the net force is 0. Likewise, the net moment is 0, since it's not going to be moving, there's going to be no net force or net moment on it. So we're really more so concerned about the net moment, because if we were trying to just look at the net force, you would get some kind of amount of reactions from the pivot itself. So we're aiming to analyze the moment about the pivot itself, and that's nice because then you don't have to take into account the forces that act on that pivot. So when you set up the equation, you take the moment, which is the cross product of the radius times the force, so just the distance away from the pivot times the force. So in this case, it's 6 inches times 450 pounds minus 1.5 inches times the unknown force F. You end up being able to simplify that system because you know it's equal to 0, you bring one thing to the right, solve for F, and you eventually get 1,800 pound-feet of force. From that, you could do a lot of like spooky magic to just kind of see what the rest of the pressure is in the system. It's really just using like pressure is equal to force over area. But this is one of the first steps to giving people a lot better of an idea of what kind of forces they're seeing in the system. So pressing the, are you specifically referring to the 450 pounds, or are you referring to the amount of output onto the master cylinders? Because if it's the 450 pounds, I don't know. The 1,800 is actually because of the mechanical advantage that you're getting from the lever. That's really how a lot of brake pedals will work. They'll either work to increase your mechanical advantage, so increase the output force, or decrease it. And in times you'd want to decrease the mechanical advantage, so you apply less force, you'll actually make the pedal on the other end move a lot more. But it's essentially, it's like as this goes along, like as you press this, the more this will travel a lot further than this part, but it'll also apply a lot more force because of this net moment being 0. So like, again, it's just a matter of solving this equation. It just kind of ends up like, oh, you end up getting a much larger force. Yeah, whoever is applying 450 pounds to this, oh Lord. But again, it's specified by the rules, so we have to be able to prove this. So moving on to our next topic is solid mechanics. This is a very, very important one, and there are a lot of different principles from this which you really should know, especially if you're doing any of the mechanical systems. So first things first is knowing about forces and moments. So whenever you have loading on a part, it's important to know that all loading is a result of a combination of forces and moments. And it's important that you know this because you have to know what's acting on a part. There are different scenarios of loading, which I'll go through in a bit, and it's important to kind of understand those distinctions because it's really, really critical that you know what kind of loading might be going onto a part, because materials will be stronger in one way than they'll be in another. Again, stuff which I'll touch upon in a bit. For real quick, one confusion that often comes up, often moment and torque is used very interchangeably. Generally, you can get away with using one for the other, but generally what ends up being the kind of, I guess, standard or trend that I've really noticed is that moment refers a lot more towards like a thing that's like bending, whereas torque refers something to more so that's kind of like rotating or in torsion. So like, let's say if you have a shaft that's like supplying power, that will be under torsion, whereas if you have, let's say, a cantilever, like a beam that's cantilevered or something, that's more so under bending. So like, let's say if you have like a barbell, for example, the weights on the ends are applying a moment. Technically, also, you can call it a torque, but the standard in that case would be to call it a moment. So these all play important parts because they end up contributing to what's called stresses and strains. Stresses and strains are what's used a lot more in engineering to kind of explain what's happening in a part. And it's actually pretty nifty as to why. So stress is defined as a force over a unit area, kind of like what a pressure is. And they do have the same units. So in freedom units, it is pounds per square inch or kilopounds per square inch. In metric, it is pascals, kilopascals, megapascals, or gigapascals. And the reason why stress is very important to know is that essentially it's a spatially normalized force. And what I mean by that is that, again, like as from the definition, you can see that it's amount of force per unit area. But it's really, really handy for describing how much force a part can handle, or like a material can handle, for let's say, because every material can handle so much force before it breaks. And if you have, let's say, aluminum, manufacturers and suppliers of aluminum can't really tell you when your part is going to break because they don't know the geometry. Obviously, if you have like a 1 foot wide diameter, or yeah, 1 foot diameter piece of aluminum, if you pull on it, that's going to take a lot longer and require a lot more force to break than, let's say, a 1 centimeter thick piece of aluminum. So it has kind of that benefit of, it gives you a bit of a standardization. So it tells you that like, oh, if you have a part that's 100 square inches in cross-section area, how much force is that going to be able to take? And that's where it's really, really important to use. And again, strengths for materials and such are given as stresses, not forces, because of the unknown geometries. Similarly, you also have something which is called your strain, which is the amount of elongation relative to the length. So kind of similar to what stress is, strain is actually also a normalization. In this case, it's of elongation to the part's length. So essentially it tells you again, how much stretch is there per unit length. So, right, it's a lot different if you have a 20-foot piece of something that stretches only like a millimeter, whereas it's a lot different if you have like a centimeter thing which stretches like a millimeter. Because like let's say I'll change the first thing to a meter. Let's say it's a meter, that thing is only stretching by like 0.1%, whereas if it's a centimeter, it's stretching by 10%. That's a really huge difference, and it's important to know that. Essentially, also, if you take your strain and multiply it by 100%, you get the percent of which the part is stretching. So for what are known as elastic materials, which are ones that are a bit more stretchy, I guess the better term to use is, I guess, ductile. Stress and strain increases linearly, though only up until a certain point. Taking a look at the graph over here on the right, you can see that this is the graph of stress versus strain. You'll, especially if you're in mech, you'll be seeing this graph probably like 1,000 million trillion times. You'll eventually get tired of it and you'll be like, boo. But I just want to go over it real quickly because it is important to kind of understand. For some amount of time, a part will stretch linearly with the amount of force applied, kind of like you would with a spring where F is equal to Kx. All metals are, like all kind of materials up to a certain point technically are to an extent springs, and essentially the equivalent of the spring constant is characterized by the Young's modulus of this, which is just the slope of this graph. At a certain point, you get to your yield strength, which is when you start to actually permanently deform the part. And then up to a certain point, you reach your ultimate strength, in which things start completely failing, and then you eventually fracture the piece, and that's when it fully fails. Technically, as soon as you start yielding, the part fails. As for different types of loading, so pretty much all forms of loading can really be boiled down to really 3 different main pure scenarios. So you have tension, which is when a part is being stretched. So like, let's say if you have a rope or a rubber band, or let's say, and you stretch it, that's undergoing tension. Whereas if you took something and started squeezing it, that's compression. And then you have shear, which is kind of a, so actually with tension and compression, one of the important facts about it is that the forces are kind of aligned, or like, I guess to an extent, collinear. So like you can see with the diagram on the bottom left, that's really what separates them. The difference with shear is that they're misaligned and they're going in opposite directions. So in the case of shear, kind of instances where you would see that would be like, if you ever seen like crystals just kind of like fracture really cleanly, the reason why they fracture is because of shear stress which is put on them. They kind of just separate. Other things in which you'd see shear would be like using scissors, because the kind of like the blades are slightly offset, so they're kind of applying that non-collinear forces. With those 3 in mind, all forms of loading are pretty much going to be some kind of derivation or combination of those 3. So probably the 2 biggest kinds that you'll see are bending and torsion. Bending is when you have a part that's supported at some point and then have a force being applied onto it like relatively far off that causes the part to undergo tension, compression, and shear. And so kind of taking a look at this top right thing, this is a finite element analysis, or like a stress analysis done on a part that I decided to whip up really quick. It's supported the opposite ends, and then it has a force going down in the center. This is known as 3-point bending because there are 3 points. So you can see that so with any of these kind of stress analyses, the general scale is blue is least stressed and red is most stressed. You can see that there's a lot of stress kind of happening in the top center and the bottom center. With bending, it's very important to understand that this concave part is undergoing compression, whereas the convex part is undergoing tension. And more often than not, you'll get failure at either of these 2 points. There is also some amount of shear that happens because you're just kind of having misaligned forces, but usually the main factors in bending are typically more so tension and compression. Then you have torsion, which is something that we also have to deal with a lot. Torsion is when you have, again, something which is kind of twisting, and that actually what that does is that it applies shear to that part. You can essentially break that, like, let's say the cylinder is kind of broken up into a bunch of smaller discs. Those smaller discs are actually kind of like rotating against each other and kind of all applying that like wacky non-aligned force. So usually when you have a part under torsion, it's going to fail because it'll snap due to shear. Yes. So before I go on quickly, does anyone have questions about what I've talked about so far? It's a lot to kind of take in. And again, I don't expect you guys to just have this mastered by the end of this lesson. Just, again, knowing that these things exist. All right, I will take that as a no and continue to move on. All right, so in terms of how things fail under these loading methods, so under tension, things will just yield or like they'll experience what's called necking. So in this diagram here, you can see that as the thing stretches, the kind of cross section thins out. You can see this with rubber bands as you stretch them out, how the center starts to really like after a while, you'll see that the center is really starting to thin out and then it'll kind of just break there. That's necking. Likewise, then you have kind of the opposite with compression where you'll either have buckling or barreling, where essentially with buckling, you end up having like a lot of compression and it kind of just like bends at a certain point, then it just fails. With barreling, you end up actually getting a widening of the cross section before ultimately cracks kind of form. Kind of like how if you take like Play-Doh and then squish it on itself, it starts to widen out. Not necessarily the same thing, but generally like that's geometrically what will happen. Shear, it kind of just fails just by shearing. Generally, a shear failure will happen kind of along a plane in an ideal material, so kind of like you see on this picture on the top left over here. Likewise, you can also see that this beam, which was undergoing some amount of shear, fails along this line, or like plane, I guess. All right, so another very, very important thing to understand, and we've actually had a lot of failures, which I'll talk about in a moment, due to stress concentrations. So stress concentrations are essentially just geometric irregularities in a part, and this results in a localized increase of stress. So if you have a sudden change in shape of something, it's going to cause a lot more force to kind of have to go through that sudden change. And more often than not, it's a likely spot of failure. And especially if there's already a failure, like a crack, a notch, or a scratch, they're likely to propagate and cause additional failure as like any imperfections themselves are stress concentrations. That's why when you have like a piece of like glass that's kind of starting to crack, the crack will continue to propagate because that's where you'll see the most stress in the part. Kind of looking at some examples of this. So a very common stress concentration that you'll see is if you have like a shaft where there's sudden step down. You want to avoid generally avoid that abrupt step down, and because that concentrates a lot of force to where that like inner corner is. If you build it, that actually helps out quite a lot. Generally, it's best to kind of imagine these with like stress or force flow lines going through the part. You can see on the bottom left, it's very concentrated there, whereas with the fillet, it generally helps smooth it out a bit more, so it experiences less stress. Because again, if you have a lot more force going through a smaller unit area, that's going to create a lot more stress and induce failure. Likewise, let's say if you have a hole going through a part, that's going to cause a stress concentration on all of the corner, not corner, but like the top, bottom, left, and right edges of the part, because there's going to be so much stress kind of built up there. Yeah. So in terms of stress concentrations, kind of even showing you from a simulation standpoint, this is a 1-inch square cross section of aluminum. Right now, there are no parts of which are failing under I believe, a 30,000 pound force tension. Again, no part of it is failing. Everything is green and it's below this like little red arrow, which indicates at what point the failure is or the yield strength is. So in this case, it's 2.75 times 10 to the 8th pascals. However, even if we had the same cross section and now added on these wacky supports, you can see that these inner edges are not at all filleted. And this creates a lot of stress concentrations and increases the stress greatly at the edges. Now you can see that you have a little small red areas at the very corners. These red areas are above this little red arrow, which indicates, again, the yield strength. So this is where the part is going to fail. Again, this is the same cross-section, and this is the same amount of force being applied, but this creates a significantly higher stress in that one region, which will cause it to kind of, well, in this case, fail. In terms of where we've seen it on the car, one prime example is what's known as our spindle, which is how we attach our upright to our hub, or I guess hub to upright technically. When this is supposed to be made, there's actually supposed to be a gradual taper step down here. As it turns out, when it was manufactured, this taper was actually slightly larger than it was supposed to be and created a bit of a kind of sudden step down like you would see over here. And there's actually a lot of load which goes onto this point potentially. And so if you kind of look in the left photo real like close, you can actually see that step down occurring. And so essentially at some point the car kind of went a bit off track and hit something, and that hit went directly through the tire, and the tire transmitted the force onto the spindle. And the failure, you can see, actually starts basically right at that step down. And it caused the piece to kind of just shear and just completely fail. So this is kind of like a lesson in, you just have to be careful not just with your design, but also with how you make the part, because in the end, you might not get something too ideal. Likewise, you have another part here, which is our hub. Our hubs just generally tend to fail because there's not actually much material. But part of that is actually they always tend to fail around these holes over here. When they fail, part of it is because of the stress concentration. You can actually see that it fails almost perfectly along where the like that edge of the hole is. There was also other reasons for this failure, which I'll talk more about in a bit, but that was part of the contributing factor. So it's not like why it failed, but it explains where the failure started, if that makes sense. In terms of the question of where is the force being applied, for which thing was that? Oh, okay. So on the aluminum part, it's just being applied at the very end. So like on this flat face. So imagine if you have like some super strong adhesive or something, which is applied to it, and you're starting to pull. Likewise, it's the same here, where you have the forces are being applied on these giant flat surfaces. Well, technically, one is just a fixed point, one's a force, but pretty much all that. So, cell mechanics is definitely the biggest topic, so we're already actually a good amount of the ways through. The rest of the topics are relatively small, but linkages is a very important one to also kind of digest. With linkages, you see it everywhere, especially on the car. Probably the biggest examples are the suspension and the steering, where basically the entire system is, our entire suspension is a linkage. Whenever you're talking about linkages, it's important to understand the difference between kinematics and kinetics. Kinematics is the study of the motion of it. Kinetics is the study of the force going onto it. Both of these are very important in their own rights. With kinematics, you want to make sure that your suspension is behaving properly and that the wheel isn't like, let's say if your suspension goes up, you don't want the wheel to kind of turn a wacky way. With kinetics, you want to ensure that like any forces being applied to the linkage aren't going to be like bad at other parts. With linkages, you have this concept of what's known as the degree of freedom. And essentially with the degree of freedom, it is really explains how free a thing is to move. And essentially the best way to describe it, I guess, mathematically is how many variables are necessary to define the system. So kind of bringing this over to some examples of types of joints. If you have a hinge, that's a single degree of freedom joint because it can only rotate. So in theory, you only need to define its location with a single angle. Whereas if you have something like a slider, like a slider on a plane, it can go in 2 dimensions. Or if you have a slider on a hinge, that's technically a 2 degree of freedom thing because a slider can go like a slider on a hinge that's going only moving in a line. It moves along the line, so you need a variable to define where it is along the line. Likewise, you need a variable to define the hinge. Another very prime example of this that's especially prevalent with suspension is the ball joints. Ball joints, which are kind of pictured here, is kind of a ball or a sphere that's sitting in a cup that can rotate. You need 2 angles to define its location properly. And this actually does have a lot of, the degrees of freedom have a lot of effect on kinematics. There are also different types of linkages. Most of what we focus on, especially in classes, are 4-bar linkages. The front suspension, which is a short, long arm suspension, technically is a 4-bar linkage. There are various types of these, which kind of shown up here. Different types aren't really that important to know in our context, but they allow different types or ranges of motion. Again, here's a very good example of linkages, which is our front suspension. This is a 4-bar linkage because it has 4 links in it. One link is the upright, which is at the end of the control arms. Control arms are what goes across. And the 4th link is technically the grounded link, which is essentially the link that doesn't really move, and that's the chassis. So all in all, it has 4 links, and this allows it to kind of go up and down. And with a 4-bar linkage, you can get a very precise control of the angles. So with suspension, one of the things that you're worried about is what's called your camber angle. That's the angle of the tire with respect to the vertical. Essentially with that, you want to have a very, not just like specific camber angle, but also a change with it. And depending on the geometry of the linkage, you're able to control that relatively precisely. Moving on to machine elements. Machine elements are very important because that's very much what powertrain focuses on. The biggest things I'll be discussing are gears, belts, and chains. There are other things that are also very prevalent, but this is what a lot more what we're focusing on. With all of these, they're meant for changing the axis of rotation of an assembly. Likewise, also changing the speed and torque. So kind of going through each of these, gears are amazing for short center centers because they have to directly mesh with each other. If you want a large center to center, like 20 feet, can't really get that done easily or conveniently with 2 gears, because then you need giant gears that are able to span and meet each other through that 20-foot distance. Gears are great for handling high torques and speeds because generally they're made of steel or other relatively strong metals. Gears can be broken down into spur gears, which are the typical like ones that you think of, which are like the flat ones that kind of just mesh with each other. There are helical gears where the teeth aren't like flat, but they're more like rounded, and I'll show examples of these in a bit. Yeah, that'll miter gears, which are meant for changing the angle of the rotation. They kind of fit each other at like a 90-degree angle generally, sometimes a bit off. You have a rack and pinion, which is actually what we use in our steering. It allows you to change rotational motion into linear motion. And then worm gears, which allow you to change the axis of rotation, but not have the two axes be intersecting. So again, this top left one is what's called the spur gears, and you have helical spur gears on the bottom left where the teeth are a bit more angled. This allows you to transmit a bit more force through them, which is something that can be very nice because then you can get more force for a smaller unit. These on the top are helical bevel gears, or helical miter gears technically, but miter gears are a type of bevel gear. As you can see, their axis of rotations intersect, whereas something like on a worm gear, the axis of rotations don't actually intersect. They're slightly offset of each other. The bottom right one is a rack and a pinion. You can see the square rack here. It's moving back and forth like left and right, which translates the linear rotation. Sorry, which changes the rotation to linear movement. With belts and chains, you have a lot of them just generally being really good for longer center to centers. With belts, you essentially have like a long piece of rubber which wraps around like some kind of like a cylinder, which by friction generally, in some cases not, transmits torque. Their belts are generally good for handling lower torques but high speeds. Examples of belts are flat belts, round belts, V-belts, timing belts. I'll show these in a bit. Chains, a lot of you are probably a lot more familiar with, especially if you have a bike. That's really what gives you power from the pedals to the bike wheels. Chains are also good with long center centers, and because they're metal, they handle higher torques, but because of how they're constructed, they're not the best with high speeds, and generally you want to keep the speed low. Really, the type of chain that we'll only ever use would just be roller chain. So this top left one is an example of a flat belt, where essentially it's literally just like a flat piece of rubber with possibly some kind of reinforcement in it. All the power transmission is done through friction. Likewise, over on the top here, you have round belts. Those they have a cross section where they're round. The bottom left one is what's called a V belt, and it's kind of shaped like that because it kind of has that V shape, I guess you can see. This is actually what's used on our CVT. And then you have a timing belt over here, which is actually a tooth belt, which goes onto a pulley with, also with teeth. These are nice because then you don't transmit power through friction. You actually have power transmission through the force of the pulley onto the belt teeth. We actually use this on one of our powertrain elements, which is our intermediary belt box. Lastly, we have chains on the top right. Chains, as you see, again, are these metal links, and then they sit on sprockets of which have teeth, and that's really how the power transmission happens. The reason why these are good for longer center centers is that you're able to make these belts or chains generally fairly long, and it's all right. Some very quick important concepts that I want to go through for all of these is really the biggest thing is what's known as the pitch, circle, or diameter. For gears, imagine if you had just two flat cylinders rolling against each other and applying friction. That's how they roll together. That's what the pitch circle is. It's the kind of the equivalent of those two. It's like the equivalent cylinders that you would see on the gears. It's essentially where all the force actually is being applied on the gears onto each other. In the case of belts and chains, it's generally where the what's known as tensile members are. So if we go back a slide, if you look real closely with the V belt, you can see kind of along the top here, there are some kind of like intersecting like dots. I don't know if in this case it's specifically the tensile members, but with these rubber belts, you'll often have like small, like thin cables of steel or carbon fiber going through them. In the case of chains, it's just along the center of the chain. Pitch circle can be a bit hard to get at first, but it's fine. Pitch circles are important because the ratio of their diameters is what creates reductions in ratios. These cause a difference in pitch diameters cause a change in speed and torque. So let's say in the case of the top right image, the top gear has 11 teeth and the bottom has 18 teeth. This means that there's going to be 11 to 8 ratio or 8 to 11 ratio for the top right, depending on which one's the input. And so with that, that also comes with the associated pitch, which is how many things per unit diameter. In the case of gears, it's how many teeth do you have per, like, let's say diameter, or in the case of, let's say, fasteners like bolts, how many threads per inch. Two gears, or actually, gears, pitches, chains, and belts will only mesh and work properly together if they have the same pitch. So because they have the same pitch, that also means that you're going to have, let's say in this case, the number of teeth is also proportional to the diameter. So in this case, let's say this was an 18-inch gear. This would be an 11-inch gear. Lastly is the pressure angle, which is the angle at which the gears apply the force on each other with respect to the either the horizontal or the vertical, as long as you're making sure to take the right one. This one's not as important to know, but it's just know that the standard is generally 20 degrees, and I believe that's what we use on our gears. Okay, I believe this is our second to last topic. These last two ones should be relatively quick. What methods of joining? They're really important because you want to know how to put two things together. A lot of what we use are screws, nuts, and bolts. These are not permanent in that they can be reused, generally taken off, put back on with no trouble. They're good for things that need to be swapped out. So if you, especially if you have a part that you know is going to break a lot, you might want to just use bolts and nuts to kind of fasten those together. You have things like rivets, which are permanent, but are much better for things that just generally need to stay together. Welding and brazing is when you take two pieces of metal, in the case of welding, and literally fuse them together. As you can imagine, because they're literally now the same thing, it's pretty permanent. And these are, welding and brazing is great because you can attach things at all kinds of wacky angles. As long as they're generally touching and you can melt them two together, they should be good to go together. Press fits are essentially when you have a part going into another that's too big. So like, let's say if you have a 1-inch shaft which goes into a 0.999-inch hole, it's slightly bigger so that you technically can force it in and it causes the shaft to shrink and the hole to stretch. The permanence of this depends on the degree of the press fit. So obviously if you have something where like the difference in diameters is only like 1/1000th of an inch, that's going to be a lot different, where if the difference in diameter is like 10,000th of an inch. Last thing is adhesives. I mean, pretty much everyone's aware of it. Technically, they're permanent. They're often not too strong, so that we don't really use it as often in our stuff. kind of bringing this back to the previous example before of the hubs, one of the really big reasons why this hub failed is because of a press fit, which was too extreme. If I recall correctly, the final, what the hole was supposed to be like 0.37, but it was actually drilled out to 0.32. So the part that was going through it was like 50 thousandths of an inch too large, and that caused a lot of stress. Whenever you put a press fit into a part, that causes some amount of stress to kind of constantly be there. So in addition to the stress concentration, which is already there, there's already a lot of stress there. So as soon as like there was a force on it, in this case, the car landing on one tire, it immediately failed. You can kind of see that along this edge of the piece, you actually have a lot of buildup of material, and that's because the press fit was literally, at this point, forcing material through and pushing it to kind of pile up. Long story short, know your press fits. There are standards for it. Not important to discuss now, because those can just be looked up, and something that you'll probably, if you need, we'll go more into details too with your systems. So, thermo and fluids, last thing, this is very quick because we don't actually do all that much of it. Really what it boils down to is you have three important concepts with thermal fluids that you want to take with you. First of which is that hot things expand and cold things shrink. So this is a lot more useful for fabrication. Let's say if you want to get one part off another that's press fit, if you heat up the outer part, it actually expands and thus becomes a lot looser. It's also really important for when you're machining, especially if you machine a part and it's too hot. As the part cools down, it'll shrink and you can get a part that's really undersized. Not as important for us, but especially if you're going for something, let's say like aerospace manufacturing, very important. Hydraulics is another important concept where essentially the really underlying principle behind it is that all liquids are generally considered to be pretty much incompressible. So that means if you apply pressure on one end, same amount of pressure is coming out the other, so that essentially the pressure throughout the fluid is constant. This is very important when it comes to brakes because you're able to get a lot of mechanical advantage because of it. If you know that the pressure is a force over area, changes in area of the liquid result in different forces. Taking the example on the right here, a small piston, if you apply a decent amount of force in it, because the area increases, you're actually going to get a lot more of an output force on the other side, right? So if you have 1 pound with a 1 square inch on the left, if let's say the area of this is 3 square inches, you need to have the same pressure throughout. So that becomes a 3 pound force. Very, very useful for something like brakes, which I'll talk about in a moment. The last thing generally with thermal fluids is that there's going to be a lot of also like heat transfer stuff, which can be very important, especially for something like the CVT, where you want to be able to cool it properly. There's a lot of spooky magic which goes on there with regards to making sure that you have the proper amount of airflow going through a system to make sure that's properly cooling. Moving on to brakes, a bit of to what I described before. Really, the working principle of brakes is, especially on a lot of cars, is your hydraulics. For a lot of cars, they'll operate disc brakes, which is also what we use, where again you have a caliper with pistons and pads which presses on this rotor, which is attached to a hub or an axle and stops rotation. This pressure is built up through the master cylinder, which through this wacky diagram, it essentially just creates pressure in the brakes. Yeah, so that's really all I have for this. I apologize for the information now, but it is very, very important that as many people know these things as possible. Again, not even necessarily that it's important just for mechanical people to know this, but for software people, especially let's say if you're doing software and you're going to be making the suspension simulation program, you want to be sure that you understand what a linkage is and a bit of the math behind it. Likewise, if you're doing electrical stuff and you're, let's say, making a strain gauge which measures the stress on a part, you want to know where best to put that strain gauge and really like what kind of readings you'll get. This applies for a lot of these concepts, and it's very important that, again, that you know that these things exist. So, that being said, are there questions? As it appears, I have indeed lost the game, and for anyone watching, you also have lost the game. But yeah, I can understand if there's not really any questions. It was a lot of information, and again, all very important stuff to know. So if there are no questions, we can call it at that. I'll just wait a few more seconds in case anyone does. All right, I'll assume not. So, yeah, I imagine a lot of people weren't able to make it generally because of Saturday. But Saturdays are meetings we tend to do a lot more work. So with all this, again, I know it's a lot of information dump and it could have seemed a bit boring at times, but we're essentially cramming the curriculum of like 3 years into just one lesson. So a lot of this will set you up very well for the work that you're going to be doing in your systems. And again, because the recording will be posted, you can feel free to stop back at it. Additionally, I could potentially also post the slides. Actually, we can just post the slides for all the presentations for that matter. So it's something you can stop back into and just kind of take a look back in the future. So that being said, thank you for everyone making it out. I'm going to actually stop the recording. Yes, I'll be stopping the recording now.